Now that we've talked about some of the basics of hypothesis testing, we're going to move in and start talking about our first application of hypothesis testing. And this is going to be hypothesis testing using the z-test when we have one person in our sample. So I'm just going to go share my screen with you and we'll get started. Every time we talk about a new test, the first question we're going to ask is, when do we use it? This is one of the two important questions. We want to know, how do we complete the test? What are the steps that we have to go to complete the test? But before we even do that, we need to know, in what situations is this the right test for us to use? And so for the z-test with one person in our sample, we're going to use this test when we know our population mean and variance or standard deviation. Remember that if we know our variance, we can figure out our standard deviation, and if we know our standard deviation, we can figure out our variance. But we need to know one or the other and our population mean in order to use a z-test ever. For the z-test with one person in our sample, the other requirement is that we only have one person in our sample. So let's take this example. Imagine that we have a situation where a researcher wants to test the effect of testosterone, and they give one particular man an injection of testosterone. This researcher predicts that the testosterone will increase aggressive behaviors in this individual. Now we can start working through our 5 steps of hypothesis testing. Remember that our first step is to restate our research and null hypotheses about populations. When we think about our research hypothesis, this is the way we typically think about a hypothesis. This is our prediction. On the other hand, our null hypothesis is a statement that is the opposite of our research hypothesis. It basically says that our research hypothesis isn't true. It says that there's no effect. Whatever this comparison is that we're predicting, the null hypothesis says these things that we're comparing are going to be the same. When we're doing hypothesis testing, we assume that the null hypothesis is true unless we find evidence that allows us to reject the null hypothesis. I like to think of this as the assumption of being innocent until proven guilty in a court case. Just like in that situation, we need evidence in order to reject that assumption. In fact, we believe that we make this assumption so strongly that our research hypothesis is sometimes called our alternative hypothesis. This really shows that focus on the null hypothesis because the research hypothesis is actually our alternative to the null. In this particular situation, when we think about our research hypothesis and our null hypothesis, again, we want to state these in terms of populations. So for our example with the researcher giving an injection of testosterone, we first have to think about, okay, well, what are our populations? One population is men who receive these injections, this particular man. Our other population is men in general, men who don't receive this injection. And so if we restate our hypotheses about these particular populations, we can say that our hypothesis is then, our research hypothesis, is that men who receive these injections are going to act more aggressively than men who don't receive them. And on the other hand, our null hypothesis is going to say that men who receive these injections will not act more aggressively than men who don't receive them. Remember that our null hypothesis predicts our groups are going to be exactly the same. Before we move on to step 2, I'd like to take a minute here to pay attention while we're thinking about our hypothesis. Pay attention to whether our hypothesis is a directional or a non-directional hypothesis. This is going to be important around step 3, but right now while we're paying attention to our hypothesis, it's a good point to just take a minute, notice this, and make a note to ourselves. So when we get back to this idea in step 3, we already have an idea of what our hypothesis is, which category it falls in. So these categories are directional or non-directional. An example of a directional hypothesis is our hypothesis here. Men who receive testosterone injections will act more aggressively than men who don't receive these injections. A non-directional hypothesis example would be allowing people to work from home will impact their productivity. These are both making predictions, but particularly there's some key words here that tell us whether it's a directional or non-directional hypothesis. A directional hypothesis is going to use words like more or less, or bigger or smaller. We're going to make a prediction about an increase or decrease. There's a direction to it. I'm predicting in what direction the effect will be. Something's going to happen, and I'm predicting the way that it'll happen. In a non-directional hypothesis, on the other hand, we might have a word that's more neutral and non-directional, like impact, or there will be an effect, or it'll change. These are some of the keywords that suggest that it's a non-directional hypothesis. In the example I have here, allowing people to work from home will impact their productivity. I'm not saying if it's going to make them more productive or less productive. I just think that their productivity is going to be different when they work from home than when they work in the office. And so that's the key about directional versus non-directional hypotheses. In both, we're still making predictions. These are types of research hypotheses, but the idea is, are we making a specific prediction about the direction, or are we just saying we predict a difference, but we're not saying what that is going to be? For step 2, we're going to talk about our comparison distribution. And in this step, we're going to identify in each of our tests what our comparison distribution is and figure out what the characteristics are of that. And specifically, we're going to pay attention to things like the mean, the standard deviation, and the shape of our distribution. This is one of those steps that is going to continue to change. We're going to have a different set of procedures here for this step to satisfy this requirement of the characteristics of the comparison distribution for each of the tests that we'll discuss. And that's actually in part because often our comparison distribution will change from test to test. And so we'll pay special attention to this step really throughout the course, so we make sure that we remember which steps go with which test. But so we'll start talking about our comparison distribution for the z-test with one person in our sample here. When we think about our comparison distribution, we're thinking about the distribution as though our null hypothesis was true. And specifically here, our comparison distribution is going to be the population. And this is specifically in the case where we have a z-test with one person in our sample. We have one person and we're comparing them to a population of individuals. We have one individual, we're comparing to a population of individuals. And that's going to become very important, kind of that parallel between our sample and our comparison distribution. And it's something that we'll continue to return to for each test, thinking about what do we have and what are we comparing to? And again, these things have to match up. In this case, we have one individual and we compare to a population of individuals. And so in order to think about the comparison distribution, to understand this a little bit better, you can see these distributions that I have here that are overlapping. And so I have a larger distribution that's marked in red and a smaller distribution that's marked in blue. And we have 3 different possibilities here, essentially. The first, right on top, that top graph shows what the comparison distribution looks like and our sample, what these look like if our null hypothesis was true. And this shows that line that's drawn right down the center of each distribution, that's our mean. And so if these means are right on top of one another, the mean of our sample and the mean of our population are the same, that's exactly what we should see if the null hypothesis is true. On the other hand, though, we have 2 other possibilities here, and these are the possibilities that we see in the lower 2 graphs. So first, we see that our sample mean could be lower than our comparison distribution, and in the bottom graph, we see that it's possible for our sample mean to be higher than our comparison distribution. And this is essentially what we're trying to figure out. Where is the overlap? How much do these overlap? Are these that really look like the same distribution? Or do these start to pull apart in such a way where the mean of that sample is much higher or much lower, that it starts to suggest this sample that we've taken is actually from a different population than our comparison distribution, that distribution that's associated with our null hypothesis. And we'll start to kind of think about this as we move through the rest of these steps. And so in the case of the z-test with one person in our sample, We want to determine the characteristics of the population because this is our comparison distribution in this situation. Now, what we already know, what I already mentioned about the z-test, when we were thinking about what situation do we use the z-test in, it's when we already know our population mean and standard deviation and or variance, and so can figure out the other. So we already have this information. This is a very rare situation. In the real world, we often don't have this information. We don't know the population mean, we don't know the population variance or standard deviation. Later in the course, we'll talk about what we do in those situations. But for right now, we will assume that in the case of the z-test, we know this information. And so I will always have to give you this information in order for you to complete these problems with the z-test. And so in this case, we're going to assume that our mean is 8, our standard deviation is 2.5. And again, we're thinking here about these population parameters. So we're using these Greek symbols to symbolize mean and standard deviation. So make sure that you're familiar with these new symbols. And again, if you're seeing these symbols, these right in the symbol, we're marking whether we're talking about a sample, a population, or there's some variations we'll talk about moving forward that have to do with signifying other kinds of distributions. But here we have mu is 8, so our population mean is 8. Lowercase sigma is 2.5, so our standard deviation for our population is 2.5, and the shape of our distribution is normal. And so now we move towards step 3, which is to determine the cutoff score on the comparison distribution. And this is where we're going to be using our z-table. Specifically, we're going to use the z-table whenever we're doing a z-test. And this is the point that we're going to reject our null hypothesis. So this is the point that we're going to try to compare against. This is kind of our threshold here. And so we're going to use the z-table for this when we're doing the z-test. And the z-table, here's just a little excerpt of this. This is pages long. You can find it in the back of your textbook. And so you'll have this table when you need to complete these kinds of questions. And you should be familiar with this a little bit because this is the same table that we were using when we talked about z-scores and finding these percents. And so these columns should look pretty familiar, where we have our z column, our mean to z, and the percent in tail. And for this particular use of the z-table, we're really going to focus on that percent in tail column. You can ignore the highlighting right here, actually, that's on that table, but because we're really going to focus on this percent in tail column. And so focusing on that percent in tail, what we want to think about is, as we think back to our statistical significance and those percentages that we're talking about, this is where this is going to start coming in, where we're setting this cutoff score. So if I have a cutoff score that I'm trying to figure out what my cutoff score is, I know that I'm going to be working with a statistical significance level of 5%. I could look up, for instance, 5% in my tail and use the corresponding z-score, and that's going to be my cutoff score. How this works is, so right now we're working on figuring out our cutoff score, and in step 4, what we do next in just a few minutes is we'll look for our sample score. And we're then going to compare these. And so a sample score, what we get in step 4, if that's more extreme than the cutoff score that we found in this step, this is going to allow us to reject our null hypothesis. Because we're looking at 5% in our tail, this is going to correspond to a z-score of 1.64 if we looked at that particular excerpt of our table. And particularly because we predicted more, we're going to say that it's a positive 1.64 because we know that our normal distribution is going to have a plus 1.64 and a minus 1.64. We have a directional hypothesis. And so we're going to take just a minute to think about this. Again, I mentioned that this would come back, this directional versus non-directional hypothesis. And this has to do with whether we have a one-tailed or a two-tailed test. And that's going to impact the cutoff score that we use and how we find out what percent we use and looking up our z-score on our z-table. With our directional hypothesis, we know that that hypothesis is pointing in a particular direction, and that's the only direction that we're going to look in order to look for our result. On the other hand, a non-directional hypothesis means that our result can be in either direction, and so we need to look in both tails in order to see if we have a result here. And so as we're thinking about our directional hypothesis, a directional hypothesis means that we're going to run a one-tailed test. And so if we have a directional hypothesis, we have to just figure out which tail we're looking for our answer in, positive or negative. Remember that things like more or an increase or bigger are typically going to mean a positive z-score that we're looking for as our cutoff score, where things like less than, a decrease, or smaller are typically going to mean a negative z-score as our cutoff score. And to do this, we're just going to consider the language of the hypothesis. And again, thinking about, are they predicting more or less, increase or decrease? That's really the main thing that we're going to have to worry about for our one-tailed test. On the other hand, for our non-directional hypotheses, we're going to run this two-tailed test. If we have a non-directional hypothesis here's where we have to do just a teeny bit of simple math to get our cutoff score. We have to split the percent that we're using between both tails. So if I want to use a significance level of 5%, I need to divide that by 2, to divide that in half and get 2, I'm going to get 2.5, and that's 2.5% in one tail and 2.5% in the other tail. So now I have two cutoff scores, positive and negative. So I would look up the percent that corresponds to 2.5, and I would find out that the z-score that corresponds to 2.5% on my z-table is 1.96. And so now I'm going to have a positive 1.96 and a negative 1.96. And those together are going to be my cutoff scores if I have a non-directional hypothesis. And so if we look at this graph again, we can start to put this together, and we can see that in the peach that's marked 1.64, we can see that that's 0.05, that's the significance, that's where marking the cutoff score, that's coloring the rest of that tail, that's the cutoff score that we would use for our one-tailed test. On the other hand, we see colored in on both sides, negative 1.96 and down into that lower tail, and positive 1.96 and up into that upper tail. And those are colored in peach and orange. And those are marking the cutoff scores if we had a two-tailed test with a non-directional hypothesis where we have 0.025 or 2.5% in either tail. And so this is an important step, an important part of our step 3 is we're going to use that information about whether we have a directional or non-directional hypothesis to figure out what is the percent that we're using for our significance level, and then look up the corresponding percent in our z-table. The next step is going to be to determine the sample score on our comparison distribution. And here's typically where we're going to have some equation that we're using, and we're going to plug in our numbers that we have, or numbers that we've calculated from some of the numbers that we had earlier in our process when we were figuring out our comparison distribution information. And we're going to solve this equation now. And so this is the equation that we're going to use. This is the formula that we're going to use for the z-test with one person in our sample. And this is another step where for every test that we run, this formula is going to be different. We're going to have a different formula with each test, but this is the one for the z-test with one person in our sample. And so we have z equals x minus mu all over lowercase sigma. And we remember that we already have this information where mu is our population mean, lowercase sigma is our population standard deviation. We know what those are already, so you can see those there. And so we're just going to plug in our numbers. In this case, I'm going to just tell you that we know that after we collect our data, we get our results, we find out that our sample, this one individual score that we have, from our individual who had the shot of testosterone. His score on this measurement of aggression was 15. And so we can plug that in so typically I'm going to have to give you not only this population information, but also the score for the individual that's being tested here. And so we can plug in X as our individual, our sample's score here is just this one person's score. And so that's 15 minus the population mean, which is 8, all over the standard deviation for the population. That's 2.5. We can do that subtraction and we get z equals 7. Again, have to divide that 2.5 still, and we can find that our z-score now for our sample for this particular individual is going to be 2.8. And so that's going to be our answer for step 4. And last but not least now, we have to decide whether we should reject our null hypothesis or not. And so, as we mentioned in step 3, what we're going to do here is to compare our sample score, what we just calculated in step 4, with the cutoff score that we found in step 3. And a sample score that's more extreme than our cutoff score is going to allow us to reject our null hypothesis. So we said that we would use 5%, and so that was a positive 1.64 because we said that that was our cutoff score, our z-score that corresponded to that 5%, particularly with that one-tailed test. So I've marked that here on this distribution. And our sample score is 2.8. That's what we just figured out in step 4. Typically, we'll be carrying these out to 2 decimal places. I should have written this as 2.80. And I see that I've marked this here as well. And so we can see that this sample score is more extreme. It's further out into the tails than our cutoff score. And when we're talking about a more extreme score, more extreme is always going to mean further out into the tails, further out from the mean, whether that's higher or lower. And particularly in this case, though, we have a one-tailed test, so we're only looking for a higher score. If we had a non-directional hypothesis, we were using 2 tails, we would look in either direction. And if we were looking for a decrease, that would also be a one-tailed test, but we'd be looking only at the negative side. But so again, this is more extreme. Our sample score here is more extreme than our cutoff score. It's further out into our tails in the correct direction. And so here we would reject our null hypothesis.